So we talked about that number a lot, and we wanted to make sure that people understand that those were tests that were in the past, and we wanted to make sure that you understand more now what the real numbers will look like in product environment. So it's 16 million you should not have in your head, because in actual fact, the requirement is really 64 million. So you should
Yeah.
plan accordingly.
And so that's kind of the next two bullet points. And so when we say we want to protect the space of 1 million total active connections per ENI, the implication for that is that the way that we run high availability, we do something called partner replication. And so you would have one card that's active that has always a partner that it's talking to that's also active. But each card is a standby for each other. And so what that means is you inherit the flow table of the other ENIs. And so while we use this 1 million total active connections and these 32 ENIs, then when you consider HA, that takes you to needing the memory footprint of a flow table that is essentially 64 ENIs. And when you're doing high availability, you don't necessarily have to maintain everything about. Well, there's a lot you have to maintain about the ENI, but the big thing here is you maintain the flow table, even for the passive card on the active card. And so that means you have 64 million total active connections being used in your memory space on one card at a single point in time. The 1 million total active connections isn't arbitrary. That's just looking across clouds today, be that Azure, be that AWS, GCP, whatever. The total active connections for any size given virtual machine would be around this 1 million, if not more, mark. And so if you're looking for some sort of reason why we chose that number, it's just kind of accommodating where we need to be to optimize workloads.
I
And
think
so,
also, James, just one more comment, that I think that if people have ever measured this before, small VMs tend to have smaller table sizes and bigger ones have larger. So this is still like the committed average. It's not necessarily that we're going to give a 2-core VM 1 million entries in a flow table.
incorrect, yeah, there's a little bit more, there's kind of a sliding scale there, but it's maybe to make that more clear, uh, the when we want to protect this space of 1 million, but 1 million is derived from average of VM capacity across.
Yeah, because some will actually be bigger and some will be smaller. But
Yeah,
on average, 1 million is the right number.
yeah, yeah. And so the last implication is that uh, I'm not sure how deeply we've gotten into HA with this group yet, but then when an HA failover occurs, that means that the 32 passive ENI or the 32 active ENIs on your partner card move over to what becomes the primary now after a failover, and one card may inherit 64 active ENIs with 64 million total active connections. And so just without going very deeply into what policy looks like, what the breakdown of memory is in terms of mappings, routings, so on and so forth, without touching on the OS memory footprint in the Redis DB. This is, I think, some important points. So any questions so far?
James, this HA, right? ENIs are like one-on-one mapped, correct? Between active and standby. If that's the case, why would we get 64 active ENIs?
So you're correct. So in ENI, essentially, you take a destination MAC address behind your that you wish to optimize. You also like ENI mapping. You do look at the VNet ID. You do look at, I think, some of the IP addressing, and you look at the destination MAC, and that's kind of taking you to a single optimized target that you can refer to. Now we get to this 64 number because of the way that we do partner replication. And so when we look at high availability, and some of this is in Dash today, but it's something I think we'll go more into in the future. But the way that we do high availability, there's two cards and they're both active. However, one card has 32 active ENIs and then 32 passive that it's just receiving replication from its partner on. And so if the partner ever goes down for whatever reason, those 32 that were essentially just passively being partner replicated over to it, then become active. I'm sorry, does that answer your question?
Yeah, I thought like the controller will replicate the configuration on both the cards, active and standby, the same configurations, if I'm not wrong. And
Yeah, yeah.
then,
So
yeah.
I think one of
Yeah, I
the
think that
things.
what the confusion is, it's an active HA system. It's not an active passive. So
Oh, okay.
active means that
Yeah.
both of you are taking half of the connections, and
Okay.
half means 32 ENIs being active. And then once the failover occurs, of course, that's going to double. It's not an active passive, active.
Well, it's
Okay.
it's active, and essentially you're not taking, well, you can say half of the connections, but it's really the 32 active connections on each card are being replicated to the other card. So you do
Okay.
get a flow table size of or just
Well, essentially, the
64.
flow table, just to be clear, is always 64, up to 64. It's just half are being used actively and half are a backup for the other card.
Correct.
But you're maintaining all 64 million flows on
All
both
right.
sides.
Thank
The
you.
traffic just doesn't arrive. We direct traffic of like half to one and half to the other until such an event occurs, and then everything goes to one card. In the future, it will actually, we'll have ECMP to make that even better, but right now, everything will be directed to the one card. But that means that you are managing 64 million flow table all the time. Whether packets are directed towards it or not, doesn't matter. You're still managing 64 million flows.
And this is still something we want to provide more clarity around. And so think of this as kind of a first communication to the group to help really define what we're looking at. And in the future, we'll try and further provide clarity here. But we thought this was important enough to kind of explain what we were looking at and why we were arriving at the numbers we were, get this in documentation and bring it to the group to discuss if anyone had any questions.
John Carney
Well,
has a question.
later, just as an added point before John, just later just so you know, we've been looking at this from like how you use memory, and we believe that this will take up approximately 2/3 of the 32 gig of memory. So that's what we're looking at, partitioning the memory and making sure that 32 gig is enough to support this. And currently, we believe it is.
John, you want to go ahead?
Yeah. So I I have some questions. It was my understanding that like an ENI is actually like load balanced across like many DPUs. And so like it's unclear to me like the 1 million connections here per ENI, would that be like for a given ENI, that 1 million connections would be split across, 8 DPUs or some number of DPUs that are in the appliance? That was like my understanding, that there's like ECMP and it's being like, because I thought that that's
John, there can be. There can be. This is the simplest form that we could describe. This is really a memory calculation thing.
okay.
In the future, today we don't actually use the ECMP, but very soon we will be. And yes, once you go to ECMP, it means that you're going to have even more ENIs per card.
But fewer connections per
But
ENI.
you will receive fewer connections. So it will balance the same way. It's just that for oversubscription, it makes it a lot better when you do it that way, and also for redundancy. But the numbers won't change. You'll just have well, some numbers will change because you need to have space to have more ENIs, but not for more flows. The flow table, which is dominant memory user, won't change, but some of the policy tables would of course have to be increased. So that is the consideration for ECMP. And do you spread across all cards or some cards? And that's actually what the consideration is. How much memory do you use for having more and more ENI on a particular card? Yeah. Okay. A little bit more deep talk though. This is more of just giving you a heads up that this is not 16 million. Our requirement is actually 64 million. Oh, okay. And this is just showing some of the reasons why. That's all. Okay, and I have a couple more sort of follow-ups to that. Are these connections like any of the 6 or 7 services? Are these V4, V6? Does this include NAT? Is this just VNet to VNet? Like, is it like like for example, do you expect that the capacity of 64 million connections, do you expect that capacity for IPv6 flows? Do you expect the capacity of 64 million if all of the connections are NAT kind of connections? Like some connections may have require more memory than other connections. And I just want to know, do we have to assume the worst of the worst?
That's actually an excellent question. And so a lot of it is in the IPv4 space because it's in our data centers, and essentially we can control CAPA addressing. And like there are some instances where you do need IPv6. And certainly when you start having heavy requirements for IPv6, it kind of it begins to start getting into these numbers quickly. I think the 64 million is still the space we're carving out for the 7 scenarios included, right? And the other expectations around memory consumptions for some scenarios versus others, that's something we want to bring clarity on, but this is kind of our initial thoughts right now. Like we've done some analysis and we're still trying to nail down what that will look like to give you guys a little bit more clarity, but at least we can discuss this right now. So like more of that is on the way. And you're correct to assume there's more stuff that make up the entire answer than just what we're showing right now. But this is kind of the framework that will help us get to the rest. And so like as a follow-up, I always mess this up. There should be view notes. I was just going to take a quick note to dig in more into IPv6 versus v4. I think the answer is we trend heavily towards V4, but yes, V6 would eat through those addresses as well.
But also, I think the answer to that will become clearer when we define all the mapping. Something that we were discussing last night, and I was thinking about it this morning more. As we define all the mappings actually translate to how much memory is required to perform those mappings, those transformations. And yes, they will be different based on different services. So as we kind of formally define those mappings, you can actually derive them from the documents, like more formal than that. Then you could more accurately predict the memory usage. But, different mappings translate to different encapsulations, including IPv6, including NAT and all and SLB and all of them. So once we do that, you'll probably be able to calculate it much more clearly. But your question is definitely a good one.
I think it would be really useful if you could say, yes, like the maximum is 64 million total active connections, but no more than 20% of them will ever be V6. And, no more than a certain percentage of them will ever be NATed connections. Or like, it would be useful for us, like if you could like reduce like the requirement for number of V6, like where the total is still 64 million, but V6 will never be more than some percentage of that. And because that would allow us to like optimize if we just had to say 64 million and they could all be like the worst case, then that's like substantially more memory. And maybe that's not like the reality. And we'd like to just know that.
Yep.
Okay.
Yep, I think it's an excellent point, and we will work towards that. Definitely. At least one advantage we have in Microsoft is we can measure those things. So.
Yep, and I put some notes. We need to kind of characterize these connections, right? So there's a lot more visibility we want to give you, and if there are things that you think would be very relevant, breakdowns of 6 versus 4, percent NAT connections, other things like breakdown by scenario, or pieces of the 7 services that might make up the total composition. It's an interesting question because depending upon the allocation of different ENIs on a given DPU, you can have different mixes, right? And so part of that is your implementation. And then on top of that, we've kind of given some guidelines around what these numbers, what makes sense on a single unit of DPU, but there's also oversubscription, right? And so oversubscription, depending upon how much you want to move that ruler, can make a big difference in the allocation of the card. And so this is an excellent discussion, but this was also something we knew we owed the group an update, and so we'll start here, but continue to give more visibility and also provide points for feedback. So as you guys look at this, you can definitely direct the conversation and help us arrive together at the correct answers here. So even if you have any questions you haven't thought of, please do always keep them coming. If you have any advice or feedback in general, let's work together and make sure that we address concerns.
James, one quick question. So whatever the scale limit that we are talking about is all for the phase 1 requirements, or in future this might go very well higher number, right? Which do we have any max scale that we really want to achieve on the cards, or?
And we're working through that now. So there's the min and max are driven in separate areas, and we can look at different things like ACLs, mappings, routes, etc., and determine a min and a max size per ENI. And when I started talking about characterizing connections, that's some of the stuff we want to show you going forward and kind of describe what that is and why it matters.
Okay.
What Gerald brought up earlier, though, was that the flow table or your connections table is a large amount of this memory footprint. And so even looking at like the different policy and the OS space, you can expect that most likely the largest amount of space allocation comes from flow tables, proportional to the rest, of course. But yes, we do like min and max. For sure, we need to get there.
Thank you. Yeah.
Thanks, James. Appreciate your time.
Absolutely. And thank you, folks. Please do keep the feedback coming, and don't be a stranger. All right. Thank you.
Okay. Thank you. And and James, it looks like we have Andy with his hand up.
I'm sorry, I joined a little late. You may have already said this specifically. Just on the bullet point, protect space of 1 million total active connections per ENI. So basically, this is just if I understand correctly, you're saying there should be no way that one ENI eats up all the flow space and prevents some ENI from getting at least 1 million. Is that the?
So theoretically, that's actually an excellent question as well. In most cases, if we're provisioning out these cards, we might find that we're getting to some sort of optimization that we divide the capacity of the card to be able to accommodate 30 ENIs. But the implementation does leave open that you could have one ENI that scales to the capacity of the card, right? So if you wanted one super duper ENI for whatever reason, and there's valid scenarios for that, right? This maybe a stipulation here would be that there is kind of some large sizing, some large ENI sizing may consume total capacity. So like if you want to take 3264 million total active connections and take all of your CPS and make one giant ENI, that's possible. However, when you look at the workloads in clouds today, it's not always going to happen like that. And so if you're sizing realistically to your workloads, you may not have a lot of super giant ENIs like that. And so in general, this is average, right? So you may have a few outliers where you have yeah.
Maybe an example would be good, James, in that we know we haven't released it, but we have, at least for our services, different table sizes for different VMs with different numbers of cores. And the allocator, which is a higher level piece of software, which is not part of Dash, needs to decide how to pack these cards. And it will consider some level of oversubscription if necessary. But for example, it wouldn't say, I'm going to put a great big huge ENI that consumes all the space and then go put a bunch of other ENIs on the same card. The allocator would actually take that into account. It takes the constraint and then says, okay, that big VM is going to take a large part. I can't put more VMs, or I can only put 2 more VMs on it. But the allocator will decide that based on the requirement. But the average is actually quite accurate. But in practice, like there might be a VM that has 8 million connections allocated to it, and then others with to 500K because they're smaller VMs. So you have to have the flexibility to be able to do that, and you have to have some flexibility to oversubscribe because we know that it's just highly, highly unlikely that every single VM, all 32 VMs are sitting at their max connections. That's just highly unlikely. So it makes more sense to at least accommodate some level of oversubscription, which we would also set by allocating more ENIs to a particular card than the numbers actually indicate. But it wouldn't be too oversubscribed, by the way, but we may use some level of oversubscription. So the designs need to accommodate to that. You need to be able to support different numbers of connections per ENI is what it comes down to. And whatever we set, then, if you have oversubscription, there's always a chance when you go to build a flow that there's no more table left because it was oversubscribed. That's oversubscription, right? And that's what it means. But generally, we wouldn't expect it because it would never oversubscribe that much that you should ever run into that.
And go ahead. No, please go ahead.
The main point I wanted to bring up is that, in my mind, that there's a data plane requirement here. Suppose you just have two ENIs for a single card, a single device. If you want to make sure, if it's got, let's say, an 8 million capacity flow table, let's say, you, I think, want to be able to configure it, or it should operate such that one ENI cannot take up all 8 million and leave 0 left over for the other one. You want both of them to have at least a million of their own. And then there's a shared pool left over that either one of them can take, is sort of the behavior I think you want, maybe. Whatever behavior you do want, it'd be good to document for that.
Yeah, we need to document that behavior, and you're right. We need to document how oversubscription is actually, how it's implemented, and that's one possibility. What you just said there. There's some other possibilities as well. But in any case, it can't be that you get 0 for sure. Everybody needs to get a minimum, and the number that he gave you is not the minimum. That's just the average based on what we see across. That's more of a looking across all of the clouds, looking at what they offer, measuring it, and then saying, yeah, we need to support this many because that's what's competitive today. But it's not your min, it's not your max, and it has nothing to do with oversubscription. That's more of the marketing requirement, and how we get there. We still need to do some more work. But 64 million, we can tell you that we think it is realistic to have 64 million flows in a CPU with 32 gig of memory. We know that piece. And in the future, what it will, what things like you've already mentioned that will, change it a bit is, as we go to UCMP and we have to replicate more policy, we get a little bit more experience, maybe those numbers will change a bit. But right now, we believe that 64 million is achievable based on our experience and calculation.
And I'm actually curious to turn that back around to the folks on this call. Is this in line with your expectations? What amount of ENIs did you think you were going to facilitate before this presentation?
With a 32 gig card?
Correct. I just wonder if there were any pre-existing expectations that folks had done calculations on, and there was a number that they thought that they were going to be at.
I can say from our perspective, like we weren't as sensitive to the number of ENIs for the reason you said, that the memory is really dominated by the connection table,
Flow table,
and not by the ENI. So like we weren't, from our perspective, like that sensitive to the number of ENIs, but we are sensitive to the size of the flow table, and that's why any more details you can give us on like mix of kinds of flows and things like that would be helpful.
Okay, yeah, absolutely, we can do that. And the ENI number actually does become very important because essentially that's that's the number of things a single DPU or number of targets you're going to optimize becomes, right? And so there's essentially a one-to-one mapping of the ENI to the optimization target. And so it does become important fast. And I think you're concentrating in the right place for the right reasons, because it is the majority of basically your memory use. And so, yeah, let's lay out some behavior around oversubscription, protecting the space, min and maxes. Let's start here and try and set some expectations, but also learn as we go forward and give you guys a chance for input and letting us know what you think is appropriate along the way.
I have one more question. I just want to make sure I understand what you're calling like an active connection. Are you calling each direction an active connection, or you're calling like the bidirectional?
Yeah, that's exactly. So typically a total active connection is comprised of two flows in a flow table, egress and ingress, yes.
Okay. Okay.
Yeah.
Bidirectional, always.
Yeah.
Okay.
Or yeah, not real well, yeah.
I think we are also in line with the number of total number of flows bidirectional, and whether they are active, and half of them are active. Yeah, both the HA cases are okay, as long as the total number seems in line with what we are thinking. Yeah.
Okay, cool. Yeah, and
Thanks, Reshma.
yeah, we'll have opportunities to go through this in more depth very soon. And so again, thank you folks for the feedback. And I guess Christina, I didn't know if you had any more topics.
I do. I just have one. So thanks, James, for coming and spending more time than I thought you would. I appreciate your time. And I'll send out notes on to you and to the community on what we talked about. I've just been documenting in the background here. And what we were going to do is have Andy summarize what happened at the P4 meeting, if he feels like it. Andy?
Sure. I noticed, I think Alan Lowe's here, so I'll invite him to jump in. Oh, he might have left. I will attempt to accurately say things that he would agree with. He did most of the presentation on Monday.
I did attend as well, too.
Yeah, that's right. Oh, so
Okay.
yeah, Christina, you can double check. I'd mentioned a while ago that the current P4 code in the Sirius pipeline checked into the Dash repo has some keywords that are not in the P4 language standard, and I asked what they meant. And so on Monday, Alan presented what they meant and where they came from. They've been made up by NVIDIA, and they would be interested long-term if those were became part of the P4 language standard. And Nate Foster, also involved in the P4 language design workgroup, was there, and his summary I think is correct, which is the language design workgroup is fairly conservative, but they are open to things, especially driven by actual real world use cases, are much more interesting than let's say more academic use cases. And this is definitely driven by real world use cases. And the recommendation to Alan and others was to create some more similar examples other than the Dash examples for consideration going forward. I suspect that in the meantime, this could be I doubt it would be less than a 4 to 6 month process. That would be a fast track to get a new thing like this added to the language, I think, potentially. In the meantime, from what I understand from what Alan presented, there are other ways to write this in P4 that have equivalent behavior that could be used in the meantime without any problem, is my understanding.
It sounds like Alan's the man to go ask.
Yeah,
so I
so
think
a couple of things.
Oh, finish up, Andy. I'm sorry.
Well, I was just going to say that, yeah, I think Alan liked the idea of, and it's really, I think the ball's in his court to maybe come up with a few more use cases that are more varied than just the dash pipeline.
Okay.
That's all I was
Go
going to
ahead.
say.
Thanks, Andy. Go ahead, Marian. What were you going to say?
Yeah, a couple of things about that. So alternative approach that is already, it's not really in the P4 language, but it's part of the PNA architecture. This is something that we want to adopt in the shorter period of time, because as Andy correctly mentioned, the resolution in the P4 language community may take months, if not more. So we want to also try and base our connection tracking on the PNA approach. And about that, I don't know if Mario or someone from Pensando is on the call, but there is a pull request for the PNA version of connection tracking, and we need it to be updated to the latest directory structure, so it can be merged as well. And we are working on the simulator to support it. But we need to align the pull request with the current code structure.
And I also, as a side note, Mario did contact me by email recently, and I'm going to take the action item within Intel. I think we mentioned a couple months ago that at some point there's a DPDK open source DPDK backend, a DPDK based software switch that has a P4 backend, and it might be getting to the point where it's imminent that it's featureful enough to handle some of these features, but I will go double check that and get back to you on how imminent that is, whether it's a month or more.
Right. And Mario is on the call, Marian.
Yeah. Yes, and I got the message about pointing to the new directory structure. It's not really clear to me how to do it. I started looking into it. It's not really clear how to do it, but in case, Marian, I'm gonna ask you for help to do that.
Sometimes creating a new
it's a pull request
and in the old one.
Oh yeah, exactly. Maybe that's the best because it's a pull request. So I don't. Yeah, okay. Andy, I think I'll do that. I just create a new pull request starting from the new structure. Yeah, I'll do it.
Does that mean I can close the original pull request?
Well, no, maybe wait because I'm going to
Okay.
take the changes from there and put it in the other one.
Okay.
Then
I'll
I will
wait.
close it. Close it. I'll let you know.
Okay. Sounds good. Does that work for you, Marian?
Yeah, thanks.
Mm-hmm. Mm-hmm. Great. So that's what I had for this week. I believe I briefly showed, I'll show it again. Just one moment here. Share my window. So much clicking. Okay. Can you guys see my screen?
Now, yes.
Yep.
Yep.
Yeah.
Mm-hmm.
Okay, great. So again, just to summarize from the beginning of the meeting, we have what we believe are the work items for the behavioral model and a short description over on this side of the work to be done. And Michael Miele and I today will populate the assignees that we know of who had kind of raised their hand, like Venkat and Cynthia, and Venkat P, Venkat M, and Cynthia, and we'll have to assign permissions in the GitHub repo and then populate the assignee. So that's what we'll do today. And if we've missed anything or if you can think of anything, please let us know. But we have the, compare the one version to the other for the connection tracking, and then all these UDP, IPv6. The ones that have to do specifically with connection, I prefaced with connection tracking here, and then the rest of things. So NVIDIA has taken on at least 4 of these items here, row 3 and row 7 and row 9 and row 10. So anyway, we're working on that today. And that's what I have for today. Sorry if I seem a little distracted. I'm trying to figure out my Teams buttons. They've moved them around on me. So it's a layer 7 issue. So anything else
Sounds
for
good.
today, guys?
Thank you, Christina.
Yeah, no problem. Anything else for today, guys? I can give back 10 minutes and let everyone get ready for their next meeting. Or, okay. So thanks, everyone. I guess we'll go in 3, 2, 1, and have a good day.
Thank you. Bye.
I appreciate you. Thank you.
Thanks. Bye-bye.
Okay, bye-bye.